This is Gerald Friedland, and I'm teaching at UC Berkeley, and I'm also researching at Lawrence Livermore National Lab. And one of the major questions we are asking ourselves these days is, we have all these deep learning algorithms, and we can scale them up as good as we can right now. But what will actually happen if you put these algorithms into different, like an autonomous car, for example, or to make decisions for hiring, things start getting awkward because all these algorithms are pretty much black box, and we don't know what they do. They're not accountable for anything. They don't explain us anything. And so for us, the next thing is to really think about how can we make things explainable, accountable, transparent, in a way that things can make progress without us relying just on a black box. And this is going to be my talk mostly about a couple things that we did, and also that are available to try out. And so let's just dive right into it. I myself am a multimedia person. So the point is that the multimedia field has been there for a while, and then initially we started to compress videos, and now everybody can watch cinema TV, cinema quality stuff on the TV and also on their cell phone. So that's not the point anymore. And then the next stage of this was multimedia analytics, and as with any analytics task, more and more data is the most important thing. And so one thing that might be interesting for people here is we released a corpus in collaboration with Amazon and also Yahoo. It's called the Multimedia Commons, and also people might know it under YFCC 100M. And it's 100 million Flickr videos and 1 million Flickr videos with all kinds of annotation, mostly, of course, the text, title, text descriptions, but they're geotext too, which makes it very interesting, and I'm going to talk about it in a bit. But there's a lot of external annotations now as this is growing. This is why this is called the Multimedia Commons. So we all commonly contribute to the goal of making analysis on this data easier. And the interesting thing about Flickr data is it's consumer produced, and so it's not a lab recording. It's a real stuff, and we are hoping that basically we can do field studies. So instead of going out in the field and asking 100 people about something, we could just search the videos, if we could. And that's the whole point. How can we? One particular task I was working on for a couple of years was called multimodal location estimation. And that is, how do you get from an image, video, or audio to the GPS coordinate? And we actually worked on this pretty hardcore in the sense that they gave us 5,000 Flickr videos, and they wanted 5,000 GPS coordinates back. And so we did this task. We trained machine learning in various ways. And the accuracy in the end, and actually just a couple of years ago, 2012, was this. So it's called cumulative because sort of the 10-meter accuracy videos are included in the 10,000 kilometers. But as you can see, to see the percentage on the left, we got 15% of the videos within 10-meter accuracy. So believe it or not, I mean, this is 10-meter accuracy. It's like you can find out your house. We can match whatever's like around your house with that accuracy. And that is just basically one example of the power of big data. One problem that this algorithm had and still has is we don't really know why it works so well, right? We use different approaches then to start things more explainable. And the mathematical model behind this gets better too. It's like we use belief networks. And this gives you a small idea of how the inference here works. So, for example, we have Berkeley, right? So we're not looking at visual features right now, or we're not looking at audio features right now. What we're looking at is textual features. And so basically the point is, if you have an image annotated with campanile, it could be anywhere, for example, in Italy, right? But then there's images annotated with campanile Haas, And then Haas, of course, is kind of a qualifier that doesn't exist in Italy all the time. And then there's another video annotated with Berkeley Haas, and another video, Berkeley Segregate Campanile. And guess what? Now you can build an inference chain in a way that tells you that this Campanile feature might be in Berkeley. And of course, the word Campanile doesn't do anything. That's why you have to do multimodal. You have to take a look at what the image actually looks like, and then you find images that are similar, and maybe you find some sounds that are similar, and then using that really big inference graph, you can do this stuff. Sounds good, right? Sounds more explainable, but in reality, it kind of still isn't. So a typical experiment that I run is listen to this. Just basically listen. Yeah, I'm not sure if hopefully everybody heard this. Most people will say, hey, this sounds like a train. And it is, but the most interesting question is not what it is where is it? And we asked the computer to figure this out, and we trained 32 cities. And in the end, the result was, yeah, this train is in Tokyo. Highest confidence score. Computer was absolutely sure this is a train in Tokyo. And then we checked it, and of course, the computer was right. We were very shocked by this. It's like, why does the computer know, like, from just the sounds of a track so well that this is Tokyo? And I usually do this when I go to real conferences that are people in the room, and ask them, Paul, hey, what do you think? Why does this work? And most times there's no answer, except one time. One time, there's a guy coming to me after the talk saying, it's clear that's Tokyo. I'm like, okay, it's clear that's Tokyo. Why is that Tokyo? And the answer was, well, did you hear the tracks? The tracks are special because it's the Shinkansen train, and the Shinkansen bullet train is super fast, so the tracks sound different. And from all the cities that the Shinkansen goes through, which, by the way, if you take a look here, we have Tokyo, of course, but we also have Fukuoka, which is where it ends. And then we have one other city that the Shinkansen goes through. I'm just not finding it right now. But the point is, Tokyo has the highest prior, right? So if you take those cities, it's probably not Fukuoka because Tokyo has just most people. And so given the prior, and it's the Shinkansen, Tokyo is the best bet. That seems to be right. But what I asked myself is now, okay, fine. It's pretty impressive that the computer can learn these things. But I would like to have that explanation from the computer, not from basically having to go to N conferences and finally one person knows it, right? And especially, this is just one example. Again, we classified 5,000 videos, and they all had different kind of attributes, and this would take a long time to find all the people who can explain all of this, right? So the challenges are, why does an algorithm come to a certain decision? If the decision is wrong, how can we fix it, right? That's the other problem. So the typical thing is you have a car accident because of some automatic stuff, and oh, hey, we need to do a recall. All your cars are going to be fixed, and then we're good. Or, if it's human error, United dragged somebody out of the plane. Well, guess what? We're going to change the rules, and hopefully this problem won't happen again. But this is not true for deep learning, and this is not true for most machine learning algorithms. In fact, we don't know how to fix it, right? So we can maybe train with other data and then hope and pray that this is fixed, but there's no guarantee it's fixed. Before we even do that, we don't even know why this error came across. We have no idea. And before something goes wrong, it would be nice to know what the limits of this decision making is, right? So what are we actually doing? What can I describe as the specification that this neural network is doing, right? And then the other thing is, and the best thing would be if you can actually learn from the machine learner. Again, Go was solved. People solved playing Go with the computer so that actually there's no difference between a master and a really, really high up master and a computer. But if you want to learn Go now, where do you go? To the computer or to the master? Obviously, you go to the human because the machine learning algorithm cannot tell you anything. It can play against you, but it won't tell you, hey, I did this move because this is better, and also you should do that move. It can based on math, but not based on strategy and not based on something. The only way you could learn from the network is by try and error. And of course, as we know, try and error is not the fastest way to learn. It is one way to learn, but for something like Go, you definitely want to have sort of abstract knowledge like a strategy. So the scenario I came in earlier with 100 million videos, images, and 1 million videos is that we wanted to do field studies, as I said, right? So one of the pains is to study children. And it's a pain because, of course, children don't behave the way they usually behave when they're in a lab. But then also we need permissions, all kinds of bureaucratic permissions, and both the children as well as the parent need to find the time. So if you want to study that, why don't we just use videos, right? Because videos are the natural environment of the kid, and we can just go ahead and try to see what kind of videos have been uploaded, right? And one interesting thing would be to study how do children catch a ball, right? And so we see 3 children catching a ball here or throwing a ball. So the idea is, how do children catch a ball? Let's study that. Before we even go there, how do we find those videos though, right? Because finding videos of catching a ball sounds the right way to go, except then we can't find them because the Googles and Flickrs of the world are not created for finding the videos in this way. You know, if you enter Miley Cyrus, you'll find a lot of Miley Cyrus, but you don't find children catching a ball. That's the problem. So one way you could do this now for finding these videos is you could build a classifier, right? And we've done this. So these are things that we've done to find videos catching a ball. But now here's the funny thing. How do you train a classifier to find videos catching a ball? Well, you need to train it with videos catching a ball. So how do you find those videos? Well, you know, you see the catch-22, right? Having said that, one way to circumvent this in science is, hey, have some other people find those videos for you, and then we train the classifier, and they evaluate us on how well these classifiers work. And this has been done. So this is TRECVID MED at NIST, and they gave us videos of like, hey, here, board tricks, feeding an animal, landing a fish, wedding, woodworking, birthday party, changing a tire, flash mob, and so on. And we trained on them, and train here says how many videos we used. And then the question is, how many videos could we retrieve? You know, some of them worked, some of them don't. But the general problem was, hey, if you just put the video into a classifier, there's so much noise, right? I mean, just those 3 images that you saw that are different, it's just completely different. What are the cues that the classifier would take? Of course, the typical deep learning approach is to just say, hey, just add more nodes, just make the whole thing deeper, and maybe it'll work. And the answer is it probably will. Just put more compute into it, you know, and make the whole thing even less understandable. So the problem though is in this particular example, we have another issue. So how many classes do we do, right? How does this idea scale to text search? Again, the question would be here, how much work is it to train a video of children compared to actually inviting the children, right? And it seems right now that's almost the same amount of work. And then the boundaries are clear. Which videos are really children catching a ball, right? So is it children like below 12 or below 6 or like just learning? What is a ball actually? What is a medicine ball versus a basketball versus, you know, something? So this has to be clearly defined. And let's say all of this works. We still don't know why it works, and we don't know the limits of all of this. Unless somebody wants to look at all these videos and say, haha, yes, no, yes, no, yes, no, we might get all kinds of stuff that we don't want. So we have no reasoning to say that this algorithm works. And again, when it doesn't work, why not? And so the idea that we had for solving this particular one was to go unsupervised, right? And what happened there is, if you look at an example video. Okay, ready? Give it a hug. Ready? Give it a hug. Here we go. Cameron. Hey, buddy. There we go. Here it comes. Yay! Good catch. Right. I'm stopping early because I'm not sure how much you see, but this is basically just one YouTube video of somebody catching a ball. And what we found out is that we could use the audio signal for the best. So the audio signal is composed of the actual signal, the microphone, the environment, the noise, and all kinds of other audio. There's also compression artifacts, etc. But if we take a deep look at the audio signal, then we'll see that there's one very specific thing, which is in the first line of our transcription, is the ball sound. In fact, if we would figure out a way to just isolate the ball sound from all of it, from like, let's say 10 test videos, we can probably find hundreds of thousands of videos just like that. The small experiment that we did where we actually analyzed this whole thing was already pretty interesting. We found way more than Google will ever find, because that ball sound, that two small hands trying to catch a ball, is very unique. Of course, however, the ball sound is really a small part of the entire thing, right? Basically, probably less than 1%. Everything else is like male voice, child's voice, child's room tone. So this is where, you know, when I say lots of noise, this is where the automatic classifiers basically fail, and with more samples and more nodes, maybe we get at this 1% distinguishment. But maybe we can do something else. And so what happened here is that we took a look at this and we abstracted small units of audio, just basically perceptually. And what happened is these units of audio would be Zipf distributed. And I have a video here which is probably hard to see. It's a video from Vsauce about the Zipf distribution. Zipf distribution is the most fascinating thing. You know, like it goes right along with, for me at least, with like quantum theory and all of this, because every single language in the world is Zipf distributed. Every single language. Basically, linguists ask themselves, do we have enough characters? Do we have enough words to already start to decipher a language? They check how Zipfian it is, right? And so that was the idea. It's like, okay, wow, we found an underlying distribution that's universal that will do something for us, right? And we found that by basically saying, hey, there's an impression of an object obtained by the use of senses, which is basically the same thing as saying, hey, this is a word, or you know, alarm clock is something assigned to the impression of senses. But the point is here, if you hear the clock, that's acoustic. If you see the clock and you try to isolate it using computer vision, that will be visual, right? And robotics, by the way, of course, uses these notions. So the idea here that we had is like, hey, why don't we extract audible units via percepts, and then we determine which of these percepts are common across the set of videos that we're looking for, but uncommon to videos that we don't want to find. And this is a very, very typical approach. This is being done in text retrieval for decades. It's called TF-IDF, which, and there's also other approaches, but the general concept is like exactly what's being done for text for a long, long time. Because again, text is also Zipf distributed. And so the idea that we had as a conceptual overview was kind of like, hey, can we do percepts extraction? And then we sort of weigh them in a way that we say, hey, so ball sound is the most important. If you find that, oh my God, you're good. But then also maybe the kid's voice would be there, because I wonder how many kids actually try to catch a ball without saying anything. And the other thing is, we should probably have some adult supervision in some way. Who's throwing, we don't know. So there's some way to that. But do we need the helicopter sound? Probably not. Do we need I don't know, to hear the sea in the background doing waves? Probably not, right? So this is where we weigh things, and then based on these weighings of percepts versus importance, we can do a classification. And of course, what we really want is that all of this is automatic, right? So we did that. We took an algorithm that we used before. It's called speaker diarization, where you basically you take an audio track and you say who's talking when. We thought, hey, can we generalize this? And we did that. We generalized this algorithm, and we used some statistical methods to basically just say, hey, this sound is different from this sound because we need more parameters to model this. If you had a model for sound A, and the model for sound B would be significantly different, so that's probably a different sound. And then you just create a dictionary of that. Basically, you have all these models that describe sounds and all these boundaries that say, okay, these models are different, and that means you get to basically a set of classifiers and a set of classified sounds. But the point is we keep the classifiers. And what's interesting about the classifiers is that these classifiers could in some way be described as like words, right? So when I say alarm clock, every one of you has something in mind, right? They think of an alarm clock. But of course, all the alarm clocks are different that you're thinking of, because probably, everybody thinks about the alarm clock they have on their nightstand, except everybody's different alarm clock on the nightstand, right? So that is exactly the idea here. So if we could isolate the sound for alarm clock, beep, 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 right? It all sounds different. So we get a bunch of models for this alarm clock, right? But the alarm clock that sound the same would end up in the same model. So now you could ask some questions, right? How many unique words define a particular concept? So the concept alarm clock is now defined by all the beeps that could be happening. But also the good news is that it's probably going to just be beeps, right? It's not going to be, I don't know, a helicopter sound, right? Or a door slamming. It's going to be mostly beeps. Of course, it could be a radio alarm clock and so on and so forth, but let's keep it to this example right now. So the major question we had is, okay, so if we do this, it's going to be a mess, right? Like, what's the occurrence frequency of this words, right? So you have the beeps and you maybe correlate them, you abstract away enough that it's really just beeps will kind of become an alarm clock. But what's the frequency then per video with enough extraction? What's the cross-class ambiguity of this? How indicative is this? All of this when you abstract it away, and it started to be a mess. But then again, we found the solution, as I said before. Somebody pointed out to us that in linguistics, we have these same problems. We have the problem that sometimes a word describes more than just percepts, right? So some word could have two meanings, right? So, for example, nail is like fingernail, and also, the nail you put in the wall. And sometimes different percepts are described by the different words. So, for example, it could be a watch or a clock. Well, it's still different. But I mean, the concept is clear. You have two words for the same thing. And then sometimes you need multiple words to describe one percept. And the example that I have here is the word serendipity. Serendipity is something that pretty much only exists in English. Every other language needs more than one word for that. And they were like, oh, maybe that's kind of interesting, right? Maybe then linguists know the solution for this. Well, and of course, we're not going to go ahead and build grammars and stuff. We didn't want to make things more complicated. But what we did look at is the distribution of sort of these acoustic models. And we found that it kind of looked Zipfian. So now we just defined the math and said, okay, if it kind of looks Zipfian, maybe that's our optimization criterion. Maybe we just make it look Zipfian as much as we can by sort of wiggling around which models, what the right abstraction layer is for each of those. And if we do that, then it's like language. Then we can totally treat it like language. And this is exactly what we did. We optimized it in such a way that it looked the closest as we can Zipfian. And then we use TF-IDF, which is the intro class with this total class variance. And then we could basically classify these words. Again, these are not words. These are all sort of acoustic models. And do this. And the nice thing is now, if you have a new input video and a set of representative videos, you can ask yourself much easier, does this belong to the same set, right? So you don't have a classifier of n classes anymore for like catching a ball versus board trick versus fishing. You have a classifier for, hey, these are the words, right? So it's basically like document classification. So we could also say, hey, kind of this video is both of these, because a lot of words belong to this class and a lot of other words belong to the other class. And so all we need to do for no video is to basically extract 300 of these words and weight values. And then back then we used an intersection kernel SVM for the first experiments, and then nowadays we switched to deep learning. But what is interesting about that is that first of all, the framework was very close to the overall idea that I had in the beginning. So it's percepts extraction, Percepts selection, classification, and we just basically executed on this with the machine learning techniques. But the most interesting thing is that when we did this for the first time, we were really good. So I mean, in 2011, just the audio was basically better than the initial goal of the entire program. Later on, when things become more complicated, we tried multimodal and to try to all combine this. But I don't want to go into the details here because, again, this is just, again, optimizing error versus error rates, right? And we still don't have a real explanation. What I was interested in was, why is this better? Why can we actually say this is more explainable? And we did a very quick experiment, and that just blew me away. So what happened here is we said, okay, so as of our TF-IDF score, which is, again, the between class variance down below, and then on the sort of top is the of the fraction is the interclass variance, right? So the point is here, based on that weighing, the top one model should be very representative, right? So the best score, the top score, should really point us to the classes, or basically the timing, sort of the audios that are most representative of each of the video class. And so the way we did this is we said, okay, so we have the model, and then let's use it to classify and find the highest confidence class, sort of chunk of audio for that. And now, instead of playing the audio, let's take a look at what is the median frame at this little audio segment that just got the highest score of all of them. And let's just take a look at those. So this was working on a woodworking project. This was catching a fish, landing a fish. And this was feeding an animal. It couldn't become any more prototypical. And it was like, so we know this distinction, this sort of splitting up into things really made things so that they start to be closer to human explainability, because that's explainable. Why is that landing a fish? Well, I don't have to explain anything, right? This is because why it's landing a fish. So in the last of the 2 minutes, I just want to talk about how this could be generalized, right? Because a lot of this was now, of course, very special to the use case of this particular thing. And while we're still working on this, and I think it's very important, especially current work that we do is trying to see how field studies could really work on this. The point is now, let's talk about the generalization. So again, this is your typical machine learning experiment as you run it now, right? So you have a training step where you put the development data in, you create the models, and then you use an error metric against some ground truths to make the models the best you can. And then you use those models later in a testing stage on the right to put some test data in, and then you apply the models, and these are the results. And then you can do an evaluation. And of course, if you go to a production system, you don't have evaluation anymore. You're just hoping it works. And so now with explainable AI, what I would do is I would keep all of this workflow because nobody wants to change their workflow. And however, I would log the learning process. I need to absolutely make sure we know what's going into the network. This is kind of like having a curriculum for a network. Because think about that. I mean, you want to go to the best school. Well, the reason for that is you want your kids to the best school because you know they will learn more relevant stuff. So this should be the same thing for neural networks. And then it will allow us, when we go to the evaluation stage, that we can say, okay, so this stuff didn't work. Why didn't this work? Well, it didn't work because, for example, these neurons fired made the decision. Okay, now the question is, which data influence these neurons so that we can actually see if we change that. And yeah, it's not completely explainable yet, but it gives us way more insight, way more introspection than we have currently. And yeah, we're working on this. Stay tuned. You'll probably see some publications within this year from us. And I think with that, my time is over. Let me know if you have questions. Yeah, so more skewed towards the future. There's always sort of people who are saying, "Oh my God, robots will take over the world," and all of this. Since I'm actually in the field and I've been for a long time, this is the future. This all seems much easier than it sounds. But the point is here that the moment we start AIs being able to explain what they did to you, you become very, very close to a robot, if you just think about that. And right now, if we don't have this, we don't have accountability, we don't have explainability, I feel the future of AI might be not looking so bright because no pilot, no car, I mean, no airplane, no car, no machine that needs to take responsibility should use black box deep learners, for example, because we don't know what kind of decisions they'll make. So that's why. Does it answer your question, Najid? This is a very good question. How we can achieve accountability in the general sense. So the way I think about this is, you run a company, right? When you run a company, you're accountable. You need to account for every expense, you know, and also for any income that comes in, right? That's what you do and then every year, April 15th, you or other dates, doesn't matter, right? You put in sort of the income versus the expenses, and depending on your company structure in different levels, to the IRS, and then you pay some taxes based on that or get a refund or whatever. And the interesting thing about that is that this is accountability, right? So you're not telling the IRS why you did something. You're just telling the IRS that you did something and how what you did led to the bottom line that you're reporting, right? So in the neural network stage right now, we are in the stage where we only show the bottom line. The neural network does not show you what the steps were that led to that bottom line. And I think that's, for me, the first step. And the next step is then, hey, you need to explain why you did this, right? But again, sort of accountability is sort of the IRS level for neural networks, where you basically just say, hey, we did this and this and this, and therefore we have a bottom line. That is a good question. Whether we achieve this with neural networks, we need new primitives for this. For now, I'm hoping we can achieve it with neural networks, because if we needed new primitives, then we would have to completely change everything again, and that would not be easy. What I'm thinking is right now that this would be a process that's on top of what neural networks do right now. As I showed in my slide, we would be logging the transactions, for example, like what data caused what weight updates, right? what's the techniques are in this book Super Intelligence? We might be in a simulated reality. So I haven't read that book. So it's physically entirely possible that we're in a simulated reality. We will never find out. The reason for that is that information information itself is unobservable, right? We can only observe differences. And this is a long talk, another long talk. By the way, this is also why machine learning is so powerful. So machine learning is basically the relaxation. That means we take some data that we have and put it into a higher dimension. And in a higher dimension, and this is not a physical dimension, this is just saying we represent things and with more variables. So we represent things as more variables, and then we find sort of where we can separate these variables in the right way. And this is called linear separation. So ultimately what we do is we just transform things, and then we find differences. And so we can never argue about absolutes ever, if we can only argue about differences. So who knows what the absolute is? But this is sort of my answer to the philosophical question here. Is if you want to know more about this, there's a whole field. It's called physics, and they have pretty interesting ideas about how the world works, and they are more or less compatible to exactly these thoughts. Yeah, I'm hoping. I mean, that's all I can say to that. So can AI take on personality? If so, will the results be objective? That's an interesting question. If we can model personality, then AI can take on personality. You have to, of course, keep in mind that everything that we train, especially for supervised learning, needs sort of training data, right? And the question is, can we train that? Probably. I think, by the way, yes. The more I'm thinking about it, because, for example, actors know really well how to act personality out. So, and then also we have this now in games that some characters have personality in some ways. So I think we can definitely simulate personality pretty soon with AI. Will these personality automatically evolve? I'm not sure. How do you measure someone's visual literacy? That is a very good question. I think the way to measure a fuzzy number like this is to just make it really big and hope that, and the bigger it is, the smaller the error gets. And that means you need a lot of mechanical Turk people to sort of put stuff on a scale of what they see. For personality, the information is stored in the genes of a person, isn't it? How do you take all that history in AI? So it's not clear if the genes of a person are just completely responsible for personality. I think there's a 50-50 mix as usual. I mean, it's definitely clear you can change people's personality. You know, if something bad to them happens, for example, people change. So now, how do you take all that history, all the genes into AI? I have to tell you that I wouldn't be afraid of. The data we're tackling with, like 100 million videos, for example, is bigger than the human genome. I mean, that's bigger than the human genome. And 100 million videos is not yet the biggest even, right? So there's a lot more data that is even bigger that we're currently putting into machine learners. So that might be more of a shocker for most. It's not as diverse as genes. Well, I mean, people put actually genes into deep learners. They do that, and all kinds of stuff happens. But it doesn't mean that you put genes into a deep learner and then you have a person. That will not happen. I mean, there's a lot more transformation that needs to happen. Thank you so much for the questions. These are really good questions. And it's always inspiring. It was a new experience for me to do this, and it totally works. So thank you for listening.